Okay, so remember the right hand rule. So I don't think we're going to go over that again, but the magnetic force here will work also for moving positive charges. So if you have a positive charge moving like a proton, okay, moving this way, and you have a magnetic field going up, so that will be the magnetic field, the force will come out of your hand. If you have a negative charge moving with a given velocity inside a magnetic field, then the magnetic force will be out of your hand in this direction. If you don't like to use your hand this way, so here it could be also a moving charge, a moving positive charge. It doesn't matter because the current flowing is a flow of positive charges. If you want, you can use your fingers instead. So if you have positive charges moving this way, you have the magnetic field going this way, so that will be the force. You have to understand that this force, that magnetic force, is a deflecting force. It cannot accelerate the particle. It cannot decelerate the particle. It's a sideway force, right? It will deflect it. Okay, it's a centripetal force. Yes, we have seen that. I think that's also in the pop quiz today. We we define a physical quantity that we call the magnetic dipole. Okay, and each time you have a loop of current, so current flowing like in a circle, or it could be a proton spinning. Then you take your right hand, so it's spinning this way. That will be the north, that will be the south. So it will behave like a bar magnet, okay? But if you place that loop of current inside a magnetic field, it will be acted upon by magnetic forces. There will be a torque applied, so it will rotate in such a way that the magnetic dipole will be aligned with the magnetic field. And that will be the lowest potential energy. If it's opposite to the magnetic field, so that will be the highest potential energy. Okay, last time we talked about MRI, so you have all those nuclei of hydrogen, so protons, and they have a spin. Okay, so they're spinning and they align themselves with the magnetic field of the MRI. If you excite them with radio waves, they will flip against the magnetic field. Okay, they get high, and then when they relax, they burp out radio waves from inside you to outside, so you are highlighted by radio waves. Okay, so we talk about that. It's a review, don't forget. Okay, so here, if you have, that's the idea of an electric motor. If you have a loop of current, okay, inside a magnetic field, it will rotate for the same reason, because that magnetic dipole, okay, that thumb here, wants to align with the magnetic field. So you will have a torque, like as defined in physics 1. Okay, now that torque here is not in your equation sheet. Okay, I didn't find that equation in your equation sheet, so make sure you can add that here. Okay, so here you have the magnetic force on a moving charge inside a magnetic field, and the charge has to be moving, otherwise there is no magnetic force. You have the force, magnetic force on a current carrying wire, but you don't see here the equation for the torque or for the magnetic dipole. So if you want, you can, you should add that to your equation. Okay, so far so good. Okay, and then we talked about mass spectrometer. So again here, if you have a moving positive charge here, and it does not have to be, it could be any positive charge. So you take an isotope, you strip off some electrons, and it becomes positively charged. So let's say if you have a bunch of isotopes all positively charged, and they all have the same charge. They go inside a magnetic field. So let's review again. So this is the velocity going inside the magnetic field. The magnetic field is towards you, towards you. Force is down, so it will make that turn. The turn depends, how sharp is the turn, depends on the momentum. If you have a large momentum, which is mass times velocity, okay, it will have a hard time to make the turn. If you have a Ferrari going 100 miles per hour, because we are in Miami, so Ferrari, make a turn, you cannot make a sharp turn because you go so fast. Okay, so the radius, right, the radius of that circle depends on the momentum. Okay, so larger momentum, larger circle. Okay, and also depending on the magnetic field. If you increase the magnetic field, you increase the motivation. So you make the turn sharper. If you increase the charge, you increase also the motivation, so it's going to be sharp. So the radius is going to be the momentum, okay, larger momentum, larger curve, divided by the charge times magnetic field. That will be the equation. And that's the idea behind our mass spectrometer. You can sort out isotopes, you can find the masses of isotopes, and you can collect isotopes. So we did that last time. Okay, if you have any question, let me know. Okay, so I want to emphasize again, when you have an electric force applied to a charge, positive or negative, okay, the force, the electric force will accelerate or decelerate the charge. It will make it go faster or slower. So it works like F equals mg. Okay, so when you have a gravity, for example, you throw that notebook, it's gonna accelerate down and it's gonna follow a parabola. But there is an acceleration. The magnetic force here is a deflecting force. So the force is perpendicular to the magnetic field, perpendicular to the velocity. If there is no velocity, there is no force. If the velocity is parallel or anti-parallel to the magnetic field, there is no force. And the force cannot change the speed. Okay, so I just want to make sure you understand that. I have like a simulation. And then we have to move. Okay, so the typical pop quiz. So here you have a magnetic field inside the board and you have an electric field up. I'm going to first remove the magnetic field. Okay, so I'm going to make it 0. Okay. Okay, and no initial velocity. So you see velocity, but imagine it's not there. What's going to happen to that positive charge? You have an electric field up, F equals QE. So so the force will be where? No, there is no velocity here. It's just a positive charge inside an electric field. An electric field will accelerate, right? The force will be the same direction as the electric field. F equals QE. Don't forget the test number 2. A positive charge wants to go with the electric field lines. So if I let go, it will accelerate. You see, the speed is going to increase. It's accelerating along the electric field. So an electric field accelerates a charge or decelerate. Now, if I start again, I'm going to remove the magnetic field here. But now I'm going to have some positive velocity. It's still going to accelerate up. But now you have a projectile motion. It's following a parabola, but it's still accelerating. There is an acceleration. That acceleration is along the electric field. F equals QE. Okay, so an electric field always accelerate, decelerate a charge. If you have a magnetic field, so now I'm going to remove the electric field here. Okay, and let's say there is no velocity. So the charge is not moving. So forget about the arrow here. It's not moving. Is there a magnetic force? Can we have a magnetic force if the charge is not moving? No, thank you. No, very good. Yes, no, no, not moving. It has to be moving. There is no velocity, no magnetic force. So it's not like an electric an electric force. If it's not moving, there is no force. It has to be moving. So now I need to have some initial velocity this way. And now, you see, it's going to go, the positive charge is going around the magnetic field lines. Magnetic field lines is going into the ball and it's going into a circle. So this is called a cyclotron motion. Okay, so a magnetic force deflect a charge and make it go around the circle. See? Now, just for fun, I can have both. I can have the electric field and the magnetic field. And then you have a very interesting motion. So one field make it go faster, and one field make it go around a circle, and you have a complex motion. Okay? And of course, you want to use a textbook. If you are preparing for the MCAT, you need to open your prep book and go over, the summary and do the problem as we go along, because otherwise you're going to forget. Yes. The what? Which force? No, that will be the magnetic force. Make it go around the circle. Magnetic force make a charge go around the circle. It will deflect the charge. Right? So we did that last time. A magnetic force deflects a charge. An electric force accelerates the charge. Okay, so for example here, so I don't have my tablet. So we'll have to manage the old tech way. So you have a magnetic field this way and the charge is moving in this direction. Do you have a magnetic force? Are you sure? To have a magnetic force, the velocity, you need to have a component of the velocity perpendicular to the magnetic field. Okay? If they have the same direction, no force. If they have opposite direction, no force. Right? So the magnetic force equals 0. Okay, in this situation, you have the velocity this way, you take your right hand, again, velocity this way, magnetic force, magnetic field that way, the force is up. Okay, so it means it will deflect the positive charge up. So it's telling it you can move in this direction, but you have to take a turn. Okay, so it will go around a circle. It will go. Let's say I want to go this way. No, it will go this way. See, I want to go this way. It will go around like this. Are you with me? See, I want to go in this direction along a straight line. No, you can't. You have to go around. Okay, so it will be deflected. It's a side force, and it will make a circle. In this situation, yes, you're going to have a magnetic force because there is an angle here. So you have a component which is perpendicular. Thank you. Okay, let's try to do this because I talk, and you are spacing out. Do it. It will be more efficient if you do it. Okay, and as I told you, I don't have a... So I hope you have your slides because I don't have my tablet. So if you don't have your slide, that's too bad. You ask someone. Okay, so case number 1, they are parallel to each other. So V is parallel to B. So in that case, what's going to be the magnetic force? 0. Okay. If there is no charge, magnetic force equals 0. If the charge is not moving, the magnetic force equals 0. Okay, so if the velocity is parallel or anti-parallel to B, no force. If it's a neutron, if there is no charge, no force. If it's not moving, no force. Okay? So what's the definition for the force? F equals Q, so you need to have a charge, V, the velocity, B, the magnetic field, and then here you have the sine of the angle between the velocity and B. Okay, that's the definition. So do number B, the case number 2. Can you do it? So if you don't have the time, I'm going back here. You see, F equals QVB. So in that case, you multiply the charge, which is a proton. So that will be 1.6 times 10 to the negative 19 times the velocity, 5 times 10 to the 6 times B, which is 0.4. And then you multiply by the sine of the angle between V and B. So sine 90 is 1. So can you do that? The unit is Newton. Are you doing it? I don't have my tablet. Okay, so that will be the first case. Now, if there is an angle here, let's say 30 degrees, then you do the same thing, but you multiply by sine 30 degrees. So it's going to be Q, V, times B, times the angle between V and B, so sine 30 degrees. So it comes from your book, by the way. Did you do it or you spacing out? Okay. So you should have found, so that will be for the last case, right? Q times V times B times the sine between V and B. And you get this. Any question? If you are asked to find the acceleration, F equals ma, you just divide by the mass. That acceleration is called the centripetal acceleration. Okay, so that acceleration is it's not because the speed is changing, it's just because the direction is changing. If you have an electron instead of a proton, then of course the acceleration will be larger because the electron has less mass. So it's easy, right? You're just applying this equation. We did that last time. I should not have to review that again because we did that last time. Q times V times B times the sine of the angle between the velocity and B. So if V and B are parallel, no force. V and B are anti-parallel, no force. If the particle is not moving, no force. If the particle is neutral, no force. It's a high maintenance force. It has requirements, right? The electric force is easier. It doesn't need to be moving, and it just needs to have a charge. Okay? So lots of applications. So in the 1930s, with a big breakthrough by Marie Curie, they started to work in nuclear physics and radioactivity and radiation. And to be able to detect radiation, they built what it's called cloud chamber. So they had bubble chamber, and then they had cloud chamber, and then they have other technology. But the idea is the following. Let's say you have a big chamber, right? And you can do it hands-on. Like, let's say you take alcohol, and I will show you a video. You have alcohol and heating pad. You have a heating pad, and you put alcohol inside. Okay, I will show you what it looks like. Okay. So you can do that. You have a heating pad here. You're going to put an aquarium on top of it. So it's like your mini chamber. And the alcohol gets into a vapor, right? But it's saturated. So almost like you are in chemistry. So it's almost saturation. So it's on the blink to become liquid. Almost turning into liquid, but not quite so. And then you have all those particles coming from space. You have particles right now going through your brain all the time, coming from space, but not only coming from the bricks here. You have uranium inside, coming from the floor. Okay, radioactivity is all around us. So all those particles, they go through your brain right now, through your body. So if you have that cloud chamber, you can see that those particles going through the chamber, they're going to kick this alcohol, and the alcohol will turn into a liquid, and you will see the trace left by the particles. Okay, that's the idea of a cloud chamber. Now, if you apply a magnetic field, those particles, if they are charged, okay, because they are moving, they will be deflected and they will go around. As they go around, they will lose energy, and the spiral here gets smaller and smaller and smaller. So that opens like a huge window of opportunity to detect new particles. That was in the 1930s, and that's when they discovered the positron, anti-electron. That's what you use for PET scan. PET scan use anti-electrons. So that's how they did it. So anyway, I just want to show you this video. You could do it for extra credit. That will be worth a lot of extra credit, but it's very hard to make. I think if you're not hands-on. If you're hands-on, it should be good. Okay? So this is the saturated alcohol, nothing to see here. And then you're going to see particle coming from space, a cosmic ray, or coming from the wall. And you see it's going to make a streak. Whoops. Let's see. If you see, oh, did you see this one? This one? That one? You see this one? You see all those radiation coming through? right? It's going for your brain right now. Whoa! This one was a big one. I don't know what it was, but it's a big one, right? So all those particles, right, going through the alcohol and kicking, and it's gonna leave a streak. Just in case you are not awake, it's gonna wake you up, right? Here, there, this one, this one, this one, that one, here, there. So it's the idea of a bubble chamber. Yeah. Ooh, this big one, big one. Uh, Imagine your brain. This is your brain, okay? Particles going all the time for your brain. Oops, this one, that one. Wow. Isn't that an, ooh, this one. Right? So we can have a rave party, right? Physics rave party without music here. But it's super cool. So that was the 1930s. So, for example, typical question for test number 3, you have 3 radiations here coming, and so they are moving. Okay, so they do have a velocity, and here you have a magnetic field. Magnetic field goes from north to south. Yes, alpha particle. Do you think is it positive or negative? Use your right hand. It's deflected up. The velocity, if you stare, it's not going to pop. Nothing will pop out. Okay, it's not that AI yet. So just do it with your hand. Velocity is this way. Um, the magnetic field goes into the board. So if it's positive, the force will be up. Very good. So which one is deflected up? Alpha particle, right? Alpha particle is a positive particle because it's a nucleus of helium. It's part of, it's alpha radiation. It's if you have a radioactive decay, you can have alpha particles. It's not dangerous if you don't, if it doesn't go inside you, because it will be stopped by dead skin. Okay, alpha particle, alpha radiation. What about gamma? Is it deflected? No, but it's moving. So what does it mean? So the force is zero if it's parallel to the magnetic field. No. If it's not moving. No. What else? The force is zero when there is no charge. Thank you. So that means gamma ray does not have a charge. It's not a charge. Okay, what is gamma ray? It's a photon. It's a light particle. So it's part of the electromagnetic spectrum. You have radio wave, microwave, infrared, visible light, UV, X-ray, gamma rays, worse, worse, worse. Very, very damaging, very small wavelength. That's what you use for a PET scan. PET scan, you are highlighted by gamma rays from inside out. That's what killed Marie Curie. Marie Curie discovered radium. And at the time, they didn't know, they didn't understand how damaging radiation could be. Okay, so she was exposed to gamma rays all the time. And consequence, she died when she was 50, something like this, of leukemia. I think it was leukemia. And her hands were so damaged that when she came to the US to collect money, because France didn't have any money after the World War II, her hands, she could not open her hands. Like her hands were like this. Could not open them. So much damage was done to her hands. So gamma rays, no charge. It's a light particle. And then beta is what? Positive or negative? Negative. Okay, you take your left hand, it's coming this way. Magnetic field goes into the screen. So the force is down. It's deflected down. A magnetic field deflects a particle. If there is no charge, no force. If the velocity is anti-parallel to the magnetic field, no force. And if it's not moving, no force. So why did they call that alpha, beta, gamma? Because at the time people were very educated, they will take Latin and Greek. So instead of saying X, Y, Z, they will say alpha, beta, gamma when they didn't know. And they didn't know. They didn't know what it were. So they didn't know that was a nucleus of helium. So 2 protons. This is a light particle. And beta, you know what beta is? It's negative. What could be negative and very small? An electron. A beta particle is just an electron. A beta plus is a positron. So it smells like an electron. It looks like an electron. But it's a positron. It's positive. Okay? Yes.
Like electrons are around the nucleus, protons inside the nucleus. Where are positrons?
Positron. It's a good question. You cannot have a positron around because it's anti-electron. So if a positron comes in contact with an electron, they annihilate each other, they destroy each other. So the only way you can have positron is in the nuclear reaction, right? And that's what you use for a PET scan. So if you do to radiotherapy, for example, or if you prepare for a PET scan, so for example, if you prepare for a PET scan, you have carbon 11, which is radioactive. It's gonna decay in boron, which I think is not radioactive, and a positron. But the positron will not chill out very long. It will find an electron to annihilate. So they will destroy each other. So the idea of a PET scan, okay, I give you like a little bit. It should be in the next unit, but if someone, God forbid, has a tumor, they give that person like a radioactive tracer, right? So it's a radioactive radiopharmaceutical, so something radioactive, right? It goes inside your body, so they mix it with sugar. Okay, cancer loves sugar. Cancer feeds on sugar. So that radioactive isotope mixed with sugar goes to the tumor. Inside there, it will decay and it will emit a positron inside. The positron will find an electron inside the person, annihilate it, and it will burst into gamma rays. So with a PET scan, you are highlighted with gamma rays from inside out. And this is using positron, anti-electron, so antimatter. So nature is so well done that we have more matter than antimatter. Because if we had from the Big Bang same amount of matter, antimatter, we won't be here because they annihilate each other. You know, it's like what was Spider-Man? It had like someone anti-Spider-Man, like the clone, the evil clone. Okay, it's the same thing, right? If you have an electron, anti-electron, they annihilate each other. And they are able to make antimatter. So if you have matter like water and anti-water, annihilation. So good thing we have more matter than antimatter, otherwise we won't be here. Yeah. No, because it's positron. They're not around. Yeah, you have to make it. Yeah, like you have to make it's whole radioactivity. It's radioactive decay. And you make it in hospitals, for example. So, for example, if you want to see a tumor, God forbid, in the brain, you're gonna make a radioactive oxygen 15, okay, and the brain feeds on oxygen a lot, right? So it will go into the brain. It will emit a positron inside the brain. The positron will combine with an electron, annihilate, and it will highlight the inside of the brain with gamma rays, because positron, electron annihilate each other, burst of gamma rays. Okay, that's how a PET scan works. You don't want to have too many PET scans, because of course you are exposed to gamma rays, which are very damaging. Okay, MRI is fine, CAT scan, huh? PET scan, oh, yeah. No, because gamma ray have a small wavelength. It will be smaller than your cell, right? The cell inside your body. So it will deposit their energy, okay, inside the cell, and it will destroy the cells. Okay, so it's too much gamma rays, like it happened when they were making the atomic bomb. Too much radiation, gamma rays exposure. You don't have time to develop cancer. You have radiation sickness. You die in a few days. Right? Radiation sickness is like having, God forbid, chemotherapy on steroid, right? It's terrible. Everything inside is destroyed. Okay? I'm not saying not to take a PET scan. It's always risk and benefit. Okay? You need to do the equation to find what's your benefit, what's your risk. But you cannot have them too many of them. PET scan, because you are using gamma rays, you're going to see very, very, very fine details. I'm sure you are in biology, so you all know that if you want to see something, you need to use a wavelength smaller than the thing that you want to see. So if you want to have a very good resolution inside human body, you need to have a very, very, very small wavelength. And gamma rays have a small wavelength. So you're going to see very, very, very finely, right? You have a good resolution, but at the same time, you are exposed to a lot of radiation. Okay? CAT scan has a larger wavelength because it's X-ray, but same thing, you are exposed to something, right? And then you have MRI, radio waves, larger wavelength. So not that good of a resolution, but it's safer, except for the noise it makes. Okay, coming back. Test number 3 here. Okay. Okay, let's say the magnetic field is coming towards you. Towards you. Yeah, not kidding. Towards you. The green one, is it positive or negative? So your right hand, green is going this way, and the magnetic field. Oh, okay, let's say it's positive. What will happen? So this is the velocity. Magnetic field is towards you. So the force is down or up? Down. So which one is positive? The red one is positive, so the green one is negative. You see, it's making a bigger circle. So it means it has more momentum. It's harder to steer. So that particle here has more mass than the green one. And as it goes into a circle, right, it's losing energy. So using a magnetic field, they were able to detect new particles. That's how they found the positron. Okay. What about here? Which way it will be deflected? So cross into the screen. So it will be deflected. Up, very good. Up. Okay. So it's gonna go. I want to go this way. No, you don't. So, okay, it's gonna make a circle. It's called a cyclotron. Cyclotron motion. Okay. So this is on test number 3. I just look at it. Okay. Now remember that if you have an electric field, the electric field is not that high maintenance, right? It just needs to have a charge, and that's fine. It will accelerate or decelerate the charge. So if you have a positive charge entering an electric field, okay, there will be a force F equals QE. That force is along the electric field. The positive charge wants to move along the electric field, except it has some momentum to begin with. So you have a projectile motion. Okay, so it's like you have something you throw like this. It has some momentum, but at the same time, it's accelerating down. So two things at the same time, moving forward at the same speed, accelerating down. Same thing here. Now, this is a high maintenance force. Not only you need to have a charge, but it has to be moving. And you need to have the velocity perpendicular to the magnetic field. And the force will not accelerate the charge, it will deflect it. Okay, so again, velocity, magnetic field, the force, it has to be along a circle. Okay, that acceleration here is called a centripetal acceleration, mv squared over r from physics 1. So this force is a deflecting force. This force is accelerating force. F equals force divided by the mass. Okay? Bless you. Okay, now we already did that, so we discussed that last time, but here it's the math. The force is a centripetal force. The force is QVB, so you massage and malax, and you get this. Okay, so the radius here will be equals to momentum, because larger momentum, harder it is to steer the particle, over QB. B is the magnetic field. If you increase the magnetic field, you increase the steering because you increase the motivation. If you increase the charge, same thing. You increase the motivation, you increase the consequence, you increase the steering. The radius will be smaller and it's going to be sharp turn. Okay, so that's the equation here. If it's not in your equation sheet, add that also. Okay, so we are missing three equations so far. The magnetic dipole, the torque applied to a loop of current, and the radius here from cyclotron motion. So write that down somewhere. If it's missing from your equation sheet, you can add that up. Okay? Okay, so let's do this one. I think it's an easy one. So the magnetic field of the Earth is 0.5 times 10 to the negative 4 Tesla. Okay, so do you see that? Can you write that down? Because I'm gonna use I forgot my tablet. So it's easy, right? So the radius R, you don't see very well, right? And plus I have coffee on my notebook. Okay, the radius equals the momentum, mass, velocity. So larger momentum, larger radius over QB. Okay, so what is given to you? You have a fast electron. So if it's an electron, the charge is 1.6 times 10 to the negative 19 coulombs. And then what else is given to you? The magnetic field of the Earth is 0.5 times 10 to the negative 4 Tesla. Okay, which is 0.5 Gauss. What else? the mass of an electron you have in your equation sheet, it's 9.1 exactly, minus 31 kilogram. Okay, and what do they want? The velocity. They give you the velocity, which is 2 times 10 to the 7. Okay, so find the radius. So don't forget to frame the denominator because of scientific notation. Okay, so you multiply the mass by the velocity, enter, divide by the charge, in parentheses, enter, divide by b, enter. Okay, frame the denominator. You can do it step by step. Are you doing it? Yes, 2.27. Okay, so about 2.3 meters. Did you all get that? Yes, you're doing it? Now, question B is if the magnetic field now is 10 Tesla. So you increase the motivation, you increase the steering, so now you should get a sharp turn. Okay, the turn should be sharp. So do the computation. So you do again the mass, the velocity, enter, divide by the charge of the electron, enter, divide by 10. B is changing.
13.
Yeah, times 10 to the negative 5, right? So you get a much smaller radius because there is more motivation, more steering. Okay, you can tune the magnetic field. If you increase the magnetic field, it's going to be sharp. Are we good? Okay, if you want to convert that to 10 to the negative 6, it's going to be 11.4 times 10 to the negative 6 meters, which is 11.4 micrometers. Okay, any questions? Once a semester, I forget my tablet. And then I'm so shocked that I won't forget again. It won't happen again. Okay, so that's the details. Okay, so a very nice application is the Large Hadron Collider. So it's a particle accelerator between Switzerland and France. It's underneath, inside the ground. And you see, you have protons. So how do they get protons? They take hydrogen, they strip the electrons, okay, and then they will accelerate the protons with an electric field. So they try to simplify here. It's like you are pushing the electrons or the protons. Okay, they will make them faster, and then they make them going into a circle with a magnetic field. So that way, instead of having a linear accelerator that takes so much space, they make them going into a circle. So they go around a circle, they push them. Around the circle, they push them. And they go faster and faster and faster and faster because of the electric field. And when they collide, they destroy each other, right? E equals mc squared. And out of this energy, right, you have new particles. And that's how they discover the Higgs boson. They call that the particle, the God particle, because that explains why things have masses. So they did that big discovery, and there was a Nobel Prize. But anyway, I just want to show you. Let's see. See, that's back then. Before that, before using that technology, this is also is still used today. So you can have a linear accelerator when you are using just an electric field to accelerate a charged particle. Okay, so they used to do that to accelerate particles and then to smash them together to see new things in the making. And now they like to use for the atom smasher, right? They like to use a magnetic field to make them going into a circle, speed up, circle, speed up, circle. So linear accelerator is still used, for example, today that will be radiotherapy. It's used for radiotherapy, right? So you have an electron, you accelerate the electron is going to crash here, all that energy goes into X-ray, and you are aiming at a tumor, God forbid. Okay. Explanation. The video. Very nice video. Large Hadron Collider.
Spectacular Large Hadron Collider.
So Switzerland.
Atoms from this gas cylinder are fed at a precisely controlled rate into the source chamber of a linear accelerator, CERN's LINAC 2, where their electrons are stripped off to leave hydrogen nuclei. These are protons and have a positive charge, enabling them to be accelerated by an electric field. Their journey to eventually take part in ultra-high energy collisions, similar to those following the Big Bang.
So this is a linear accelerator. You are using an electric field. Only the electric field can accelerate a charge. Magnetic field only deflect. So linear accelerator.
This initial acceleration has caused LINAC 2 to be likened to the numbering first stage of a huge rocket. By the time this packet of protons leaves LINAC 2, it'll be traveling at 1/3 the speed of light. It's about to enter the booster, stage 2 of the rocket, if you will. In order to maximize the intensity of the beam, the packet is divided up into 4, one for each of the booster's rings. Straight acceleration is now impractical, and the booster is circular, 157 meters in circumference. In order to accelerate the packets, they are repeatedly circulated, and the electric field is now pulsed in the same way that you push a child on a swing.
So again, they go into a circle because there is a magnetic field, and then you use an electric field, okay, from a power supply to push them, okay, for them to go faster. Electric field accelerates.
Each certain point. Magnets exert force passing protons at right angles to their direction of motion. So powerful electromagnets are used to bend the beam of protons round the circle. The booster accelerates the protons up to 91.6% of the speed of light, squeezes them closer together. Recombining the packet from the 4 rings, it's then flung on into the proton synchrotron, by analogy, stage 3 of our rocket. Let's just follow 2 such proton packets. The proton synchrotron is 628 meters in circumference, and they circulate for 1.2 seconds, reaching over 99.9% of the velocity of light. It's here that the point of transition is reached, a point where the energy added to the protons by the pulsating electric field cannot translate into increased velocity, as they're already approaching the limiting speed of light. Instead, the added energy manifests itself as increasing mass of the protons. In short, the protons can't go faster, so they get heavier. The microscopic kinetic energy of each proton is measured in units called electron volts, and now the energy of each proton has risen to 25 giga-electron volts, or GeV. The protons are now 25 times heavier than they are at rest. The packets of protons are now channeled into stage 4, the superproton synchrotron, a huge ring 7 kilometers in circumference, designed specifically to accept protons at this energy and increase it to 450 GeV. Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large Hadron Collider, or LHC, which lies between the Jura Mountains and the Alps. and straddles both France and Switzerland. Lying deep underground, it has a circumference of 27 kilometers. There are two vacuum pipes within the LHC containing proton beams traveling in opposite directions. Using ultra-sophisticated kickers to synchronize incoming packets with those already circulating, one vacuum pipe has injected into it protons which will circulate clockwise, and the other protons which will circulate anti-clockwise. The counter-rotating beams cross over in the four detector caverns, where they can be made to collide. The energy of the collision is double that of the individual opposing protons, and it's the debris from these collisions that is trapped in the detectors. For half an hour, the SPS injects protons. Finally, there are 2,808 packets. During this time, the LHC adds extra energy to each proton, whose velocity is now so near the speed of light that it goes round the 27-kilometer ring over 11,000 times each second, getting a boost of energy at each revolution from the pulsed electric field. Finally, each proton has an energy of 7 tera-electron volts, and they're 7,000 times heavier than at rest. The magnetic force needed to keep the beams bending to the ring is so enormous that nearly 12,000 amps must flow through its electromagnets. This is achieved by making the LHC colder than outer space, so that its magnets become superconducting. Now the protons are ready to collide in the detector. Steering magnet finally brings them onto a collision course. The total energy of two protons colliding in the LHC is 14 tera-electron volts and reproduces similar states to moments after the Big Bang. Particle tracks from these collisions can be analysed by computers connected to the detectors, and it's hoped these tracks will give a new insight into the very birth of our universe, how our universe has evolved, what governs its behaviour today, and where it's going in the future.
So that's an old video because in the meantime they did discover the Higgs boson, and there was a Nobel Prize for that. So you can look at. Let's ask Gemini. So 2012, Large Hadron Collider, Nobel Prize 2013. Okay, it's what gives particles mass. So that's why they call that the God particle, nickname, right? The Higgs boson is the God particle, and they did that discovery in that Large Hadron Collider. Okay, it takes you to E equals mc squared. So it means energy and mass, it's the same thing. It's a different, like the same coin, different faces. So if you have mass, mass means energy. So if you destroy mass, you have pure energy, and out of that energy, you can crystallize new particles. So that's how they made this amazing discovery. It cost a lot of money to run this experiment. So I'm not sure it's still running. Not sure, especially today. You need a lot of energy, right? Yeah, I don't know if it's still running. Let's ask. Yeah, so it's running, and it's in third extended physics run, which is scheduled to continue until 2026. It will shut down for a major upgrade. Okay, good. Okay. So first of all, magnetic field going into the board. You have a proton and an electron. Yes. It's really big because it's between Switzerland and France, so it's huge. I'm not a robot. Oh, come on. See, it's huge. I don't know if you can see. It's 17 miles. 17 miles around. So it's huge. It's a tunnel. It's underground. Okay, you have here. Yes, this is Switzerland. This is France. This is French Switzerland. You have Italian Switzerland, German Switzerland, France Switzerland. Italian Switzerland is the best. Don't go to French Switzerland. Okay, I have to cut this. Okay. No, they don't. No, not nice. Okay. So they have the proton here and they have the electron. So which one do you expect to make the sharper turn? The electron or the proton? Which one has the largest mass? The proton has the largest mass, right? So larger momentum. So which one will be the sharpest turn? So the proton or the electron will do the sharper turn. Which one is easy to steer? The electron is easier to steer, right? So it should be A or C, okay? Because the proton has more mass. No, the opposite, right? So which one will? Oh, okay, I don't know. I'm tired. Which one has the more mass? The proton, right? So it has to be answer B or D or E. Do you agree? Okay, because the proton has more momentum, so it's like a truck making the turn, it's harder to steer. So it should be D or E. And then, is this picture making sense? No, why? And they go to the same direction, exactly. Is this one making sense? No. This one makes sense. Yes? Okay, so let's check. Positive B, the velocity is going this way, magnetic field is going into the ball, so the force is down. So you see it's going to turn in this direction, the electron will turn in the other direction. Electron has a smaller mass, so it will be easier for the magnetic field to steer, to bend, to turn. Okay, a Ferrari is easier to steer than a big truck. Agree? So if I give you that for a pop quiz or test number 3, you will know the answer. Okay, and then the mass spectrometer, how does it work? So this is your domain, right? In biology, chemistry, they use that a lot. So let's say, first of all, we're going to use an electric field. You're going to use a voltage, right? So you apply the voltage, you have an electric field, so the particle is going to be accelerated. Okay, so it will go inside this magnetic field region with a velocity. So again, velocity is here, and then the magnetic field goes towards you. So the force is in this direction. Do you agree? Okay, so it's going to steer in this direction, you're going to have a radius. And then what you do is that you're going to tune the magnetic field. So you're going to challenge the magnetic field until you're going to hear a click in your detector. So let's say it's an isotope and you don't know the mass of that isotope. Okay? So you accelerate the isotope, make a turn, and you're going to tune here the magnetic field. You're going to change the magnetic field magnitude because it's from electromagnet until you hear a click in your detector. Okay? And then you can find the mass. So if you do all those equations here, know that how easy algebra find the mass of the isotope depends on the magnitude of the magnetic field square. That will be that equations here. So that's how a mass spectrometer works. So that's from your test number 2. Remember, if you have potential energy, it's going to be Q times the voltage. Okay, you apply the voltage, the electron or the isotope is going to accelerate, so it's going to have kinetic energy. Potential energy turns into kinetic energy. Okay, and then you have this equation that we already defined. You take both of them, you massage, you shake it, you play with it, and you get the mass of the isotope. Okay, so that's how mass spectrometers work. Any questions? So it's a big deal in biology, for example, or chemistry, more in chemistry. So for example, you have a neon isotope. So you have isotope 20, 21, 22. So the same number of protons, different number of neutrons. Okay, and thanks to this mass spectrometer, you can not only find the mass of the isotopes, but you can find the relative abundance. So for isotope 20, for example, you're going to hear click, 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 and then 21, click, click, click. Okay, you don't have that many of them. Okay, so it's used a lot in research. And you can use this equation here. So if you have a large mass, you will need a larger magnetic field to be able to hit the detector. Okay, if you have a smaller mass, so you don't need that big of a magnetic field. So you use a magnetic field to tune, to get a click in your detector. Larger mass, more inertia, larger radius. Any questions? So, example of applications, but I already talked about that. I think I did. So uranium has several isotopes, several of them. Forgot, but two important. Uranium-238 is one isotope. Uranium-235 it's another isotope. 98% of uranium is uranium-238. And then you have like 0.1%, like very small, is uranium-235. Except that if you want to make an atomic bomb, you need uranium-235. And you cannot use chemistry, as you all know. Isotopes will behave the same with chemical reactions. You cannot use chemistry to sort them out. You cannot isolate uranium-235 using some chemical reaction that will not work. However, because they do not have the same mass, okay, a genius, his name was Ernest Lorenz from Caltech. Okay, he used the mass spectrometer to make what is called a calutron. Okay, so he used this technology to sort out uranium. So you have uranium-235, uranium-238. Which one has the more mass? Uranium-238. Okay, so when you apply a magnetic field, this one will have a larger curve, this one will have a sharper curve. And that's how they enriched uranium for the first atomic bomb that went for Hiroshima. That's how they did it. And then they changed technology. Okay, but that's how they did it. That was a big breakthrough. It's called a calutron. Uranium-235, that's what you need to make an atomic bomb. Without uranium-235, and you need to have a critical mass of uranium-235 if you want to make a bomb. That's why there is a whole thing about Iran, right? Once you have that critical mass, it's super easy to make a bomb. An atomic bomb, like uranium bomb, is very easy to do. Like any graduate students in chemistry can do it, right? The technology is not that hard. Hydrogen bomb is another story. But uranium bomb, very easy to do. And only if you have enough uranium-235. So this is called uranium enrichment. So in Iran, for example, they don't use that technology anymore. They use centrifuge. But the centrifuge is the same way. You are using a centripetal force, right? You spin the isotopes. Uranium-235 will be bent over a larger radius. Uranium-235 will be bent over a smaller radius. You collect uranium-235 and you make your bomb. Okay, as you enrich uranium, it gets easier and easier and easier, and you go faster, faster, faster to the critical mass. So that's the story of Manhattan Project. And it's called the Calutron, right? His name, the physicist, his name was Ernest Lawrence. Ernest Lawrence. Him. He got a Nobel Prize also because he worked not for the bomb, but he worked on the cyclotron that we're going to see soon. But he worked on the basis of spectrometer, so he improved the spectrometer, the mass spectrometer. Any question? Very interesting story, right? Manhattan Project. They call it Manhattan Project when they were making the atomic bomb, just to confuse people, okay? Manhattan Project. You will not guess that they were making the atomic bomb at the time, right? So anyway, so I leave you to do that on your own. That comes, I think it's part of a pop quiz. It's from the MCAT prep book that I told you about. Let's see. Let's say A is positive. Which way is it gonna go? So here, magnetic field into the board. So try your right hand. Staring doesn't help. Nothing will pop out. Okay? So moving this way, magnetic field is in the board, so it will be deflected that way. Okay? It will be deflected this way. Negative charge will be deflected the other way. So that's for people doing the MCAT. You can try that on your own, but it will be deflected this way. Okay? This one, just reviewing for test number 3 as well. It's positive. So you see, it's confusing because where is the positive? I don't know where is the positive. If this is the positive here, oh, this is the positive. Yeah, positive side, right? So it's a good ground. So it wants to rotate to align itself. So this is this one. To rotate itself to align the magnetic field. Okay. So that way you know if it's clockwise or counterclockwise. Okay, so it's number 1. Try number 1. Do it. I don't have my tablet. You have to use the equation R equals mv over qb. So do it, don't stare. Do. That's Montessori. Maria Montessori says that you have to do. Otherwise you don't learn. And that was before the phones. So try number 1. Hmm? What? Oh, it's that means 1.6 times 10 to the negative 19 coulomb. Elementary charge is like the charge of an electron or a proton. So 1.6 times 10 to the negative 19. So it could be like a isotope that was stripped from one electron. So now it's charged positively. Are you doing it or you are staring? Okay, if you stare, it doesn't help. Don't stare. So the equation is R, the radius, equals the momentum over QB. Q is the charge. Okay, so what is given to us? The radius is 35 centimeters, so 0.35 equals the mass, we don't know. And then it says 0.9 times, so 0.9 times the speed of light. The speed of light is 3 times 10 to the 8. Okay, 3 times 10 to the 8 is the speed of light over the charge is 1.6 times 10 to the negative 19. The magnetic field is given is 8. Okay, so now you can do it. You isolate the mass. What did you say? Okay, so what do you get at the end? What's the final answer? 28? Oh, 17. Okay, times 10 to the negative 28 kilogram. Okay, which is 1.7 times 10 to the negative 27 kilograms, right? In scientific notation. Thank you. Even with an I. Right, your name?
Yes.
7 point speed.
Well, I found 17. Check, maybe I'm wrong. Did you check? Are you doing it? So what did you get? That? This 66666?
Yeah.
Okay. So 1.7 times 10 to the negative 27 kilograms. Right? Make sure you frame the denominator. Right? And that's the mass. It could be the mass of a proton. Oh, it's not, it could be. It's the mass of a proton. So it's a proton. So that's how a mass spectrometer is used. Okay? Oh, I have to switch back. It's annoying. Here, what do you think? Is it positive or negative? The particle. Take your right hand. And if you don't, if it doesn't turn this way, it means it's negative. So if you have your right hand, the velocity is this way. Magnetic field is into the ball. So the force is where? Right? It doesn't fall. So it means it's negative. Or you can take your left hand. Velocity, magnetic field down. So it's negative. So the way it works, a mass spectrometer, you apply a voltage, like 150 volt, okay? You apply a voltage. And remember from test number 2, okay, you apply a voltage. So it has, the particles have potential energy, Q times the voltage. Remember, voltage is the potential energy per unit charge, okay? So it has potential energy QV. And then that potential energy is going to turn into kinetic energy. Okay, so the electric field is speeding up the charged particle, and then it will be deflected by the magnetic field. So you use the electric field to speed up magnetic field to turn. Okay, so that's what we find here. So you have a charged particle entering a magnetic field, and it was accelerated through a potential of 150 volt. You have the radius. What is its mass? So it's using this experiment here, right? You accelerate and then steering with a magnetic field. So let's see it. Okay. So first, from test number 2, Q times the voltage, so that's your 150 volt, will give you the increase in kinetic energy. Okay, so first you speed up the charged particle, and then you use a magnetic field to bend the particle. And you have this equation. So you have equation 1 and equation 2. Okay, so first you accelerate the particle, that's a mass spectrometer, and then you bend the particle with a magnetic field. If you take those two equations and you play with them using just algebra, you're going to get the equation mass equals Q radius square over, you have this equation here. Oh, you go back to slide 68. Okay, that's the radius. So that's a mass spectrometer. Okay? You know the charge of the particle because all the isotopes, you will manage to have the same mass. You know the radius because there is a detector. You know the magnetic field that you tune with an electromagnet. And you know the voltage that you have applied. So you find the mass of the isotope. So that's how the computation is done. Now you just have to plug it in. You go back to, otherwise you go back to slide, no, what's the slide? Slide 66. Okay, so the mass, I'm not going to do because I'm not sure if I did it right or not. So it will be the charge, 1.6 times 10 to the negative 19. And then you have the radius square. Radius is 0.071 square times b square, which is 25 times 10 to the negative 3 square, okay, over 2 times 150. Okay, you just apply this equation here. So you just plug it in. Okay, so, and you should find the same thing as before. I think you should find that. Any questions? So if you go back to slide 66, you see, that's a mass spectrometer. Again, you apply a voltage. Okay, so the particle, the charged particle will have potential energy going into kinetic energy, so that's that. And then the magnetic field will steer them, will bend them. So you have this equation here. If you massage them, that's what you get here. Okay? So pay attention because for test number 3, there will be a question about that slide here. Okay, it's again the same thing. It's a mass spectrometer. If you're interested, there is a YouTube video that explains that into details, and I took that picture from this video. So, but here's the idea: you have a bunch of isotopes, and they have different masses, and you make sure they have the same charge, but different masses. Okay, you accelerate them through a potential, so they're gonna speed up. Okay, but now they have different speed because isotope they don't have the same mass. Okay, so that means that if you apply the potential, the larger mass will have the smaller speed, and the smaller mass will have the larger speed. Okay, so they all have different speed, and you have them going through that velocity selector. Okay, and we'll go back to that on Tuesday, but you see that it's going to be applied by a magnetic force and an electric force at the same time, such as they will have the same velocity now, and now they can go inside your mass spectrometer and you can measure the mass of the isotopes. So test number 3, you will have one question about it. I just reviewed test number 3, so I just remember. I share with you, but don't share with anybody else.